Welcome back to CS 480-680. This is Introduction to Machine Learning as taught at the University of Waterloo in fall 2024. This is lecture 9, specifically part A of lecture 9, and we're going to be talking about maximum a posteriori as well as Bayesian inference. So this is going to be quite a big change from what we've been talking about for the last few weeks. And so I'd like to start off by making this connection very explicit. So we spent the last 3 lectures on support vector machines and some generalizations thereof. We then used the kernel trick to take advantage of feature maps to higher dimensional spaces, to learn nonlinear decision boundaries for binary classification problems, but crucially, while remaining keeping the problem computationally tractable. So these figures here show the behavior of 2 classifiers that we considered last time, specifically a classifier using a quadratic feature map, which learned a linear decision boundary for a class of that was partially enclosed within another one. And then we also had a classifier using a radial basis function kernel defined as an exponential function that depended on the squared Euclidean distance between points. So this one had a very, very local effect on classification of points nearby to those in the training data set. And then where what counted as nearby was controlled by the length scale parameter sigma. And so it would be enormously useful, though, to be able to also exploit these feature maps for regression problems. Many real-world quantities of interest can be tied to, complex interactions of underlying processes and involve nonlinear effects. For example, an example that we'll come back to a few times today, the energy generated potentially by some combination of renewable energy sources, let's say wind and solar, for some plant in a particular region of the world, maybe it follows a curve like this. The x-axis represents the time of day, where we're going from 7 p.m. in the evening through to 7 p.m. the following day. And then the y-axis indicates the energy generated in kilowatt hours between those 2 sources. And so the gray curve in this figure shows the true underlying relationship, and then the black crosses represent the observed data points. This isn't real world data, but it represents some combination of effects of solar and wind generated in this hypothetical region of the world. And then putting those 2 together, we might expect to see a relationship like this for one particular plant. So the curve shows that in the evening, we're generating little energy, drops to 0, and might even go slightly negative overnight, in which case we'd be drawing power from the grid. And then we know that generation of solar would peak around noon, but then, perhaps in this area, wind might pick up a bit later, and so we'll see a peak closer in the early evening. But the key takeaway is that no linear model of the explanatory variable, the time of day, would be able to predict the energy generation. It can't count for these ups and downs. Thankfully, and similarly to what we did with classification, we can extend the class of linear models by considering linear combinations of fixed nonlinear functions of the input variables. So on the slide here, I've got different types of nonlinear basis functions that we can use to extend these linear models to make them capable of capturing more complex patterns in the regression tasks. So just like we did with classification, where we use nonlinear transformations to create a more expressive decision boundaries, we can apply the same principle to regression. So the first plot on the left shows examples of polynomial basis functions. So each curve represents a polynomial function of the input x raised to different powers. So for example, this green curve here would be x raised to the power of 1, just a linear function. And then the other curves would represent higher order powers. So this um, the blue curve, that would be x squared. X cubed would be this yellowy gold one here. And then we've got higher and higher powers. Polynomial basis functions are good for modeling nonlinear trends, particularly when the relationship between the input and output is smooth and continuous, but not necessarily linear. The middle plot shows Gaussian basis functions. And so these are the bell-shaped curves centered at different fixed positions along the x-axis. And so each curve represents a Gaussian function centered at some value mu, and then with a variance sigma squared that controls the spread or the width of each curve. These basis functions are great for capturing local features in the data, since each Gaussian would only be, for lack of a better word, active around its center. And so by combining many such Gaussians, you can build a model that approximates a wide range of nonlinear functions. Gaussian basis functions are especially helpful when you need a model with those kinds of local peaks or dips. Finally, on the right here, we've got sigmoidal basis functions. So these are, smooth S-shaped curves. We've seen these in logistic regression. And yeah, these are defined using the logistic function to smoothly transition from 0 to 1 as the input increases. And then each sigmoidal function is centered at a different value along the x-axis mu j. And then the parameter sigma controls how steep that transition is. And so this sigmoidal basis functions are useful when the data exhibits sharp transitions, or useful to model behavior where there's discontinuities. But yeah, overall, by selecting an appropriate basis function, you can extend linear regression models to handle a much broader range of patterns and relationships in the data to get that flexibility that you need. So how can we use nonlinear basis functions to model data in a linear regression framework? So in general, you'd express your model using a linear combination of fixed nonlinear basis functions of the input features. So phi of x would be our nonlinear or our basis function, and then the weights w are the parameters that you would learn. Another way is you could assume a dummy basis function of 1, and then roll the bias into your nonlinear combination. So this is the padding trick that we've seen before. And so then, if you have that dummy basis function, then your modeled output is just the inner product between the parameter vector w and your set of basis functions phi of x. In the context of our renewable energy generation scenario, that's on the right here again. We know that the energy generated is a function of the time of day, and then the true process governing this energy generation was modeled as a linear combination of polynomial input features. So these are the nonlinear functions there. So those are the weights there, and these are our basis functions. So we essentially using various powers of the time variable, and then the true observations were the inner product of those basis functions plus the bias, and then we added some noise to actually get these observed values at each of those points. where the noise itself was drawn from a Gaussian distribution with some variance. And so, yeah, the idea is that assuming we knew the form of the true model, we could capture the nonlinear relationship between time and energy generation by transforming X using these same basis functions. And yeah, and as we argued with classification, this is still a linear model because we maintain a linear combination of the transformed features. But because the features themselves are nonlinear transformations of the input, we can capture complex patterns and behaviors than a simple linear model would. So having access to more features allows us to capture more complex relationships. But this extra flexibility, we need to use it with caution. So to see why, in this slide here, I've got three plots that show predictions made using the maximum likelihood estimate fit for three different small data sets. So the true functions are depicted in gray, and then the MLE fits are shown in blue for the three different data sets. So as you can see, each of the MLE fits captures a relationship between the energy generated and the time of day, but they're very different from one another. In the left and middle plots, we can see that the MLE fits a curve that oscillates pretty dramatically and deviates significantly from the true function, even though the data points don't seem to necessarily suggest these wild variations. So as a result, these MLE fits here would generalize really poorly to new observations. And in the third plot, the fit looks a bit more reasonable and closer to the true function. But that's only because the training data enabled fitting a model that was more representative of the overall trends. But this improvement isn't guaranteed and wouldn't hold if the training data were to change even a little bit. So the key takeaway here is that when the MLE is used with small data sets or with models that have many parameters relative to the data, the predictions can become unstable and highly sensitive to the specific observations in the training set. And when there's a large number of parameters relative to the data, the model is going to capture idiosyncrasies and noise of the training set. And this is going to be particularly bad, result in particularly large changes when the model has small changes in the training data. And yeah, especially if there's collinearity among features or when the number of basis functions in the model is large compared to the number of observations. Yeah, to boil it down, what this added flexibility, if we don't have enough constraints, we can end up allowing it to take on overly complex shapes and patterns that might not reflect the true underlying process. So yeah, we know how to deal with this problem, or one thing we know we can do to alleviate the overfitting problem is to penalize the norm of the weights, like we did in ridge regression. So here are those same curves and fits. So the true curve, the MLE fit in blue, but now each plot also has the ridge regression solution shown in orange. Where specifically I used a regularization parameter of lambda set to 0.1. So yeah, here we're penalizing large weights. With ridge regression, we're penalizing large weights. So we're effectively shrinking the model parameters and discouraging the model from placing too much weight on any one feature or data point. And as a result, the ridge regression fits, as we can see, are exhibit more robustness to those small changes in the training data. So we can see this in that the curves from one data set to the next are more similar to one another, and also the true and also to the true underlying distributions. So we would expect the resulting predictions to generalize better to unseen data. So while the ridge regression reduces overfitting by uniformly penalizing the size of the weights, it doesn't consider at all the nature of the problem that we're modeling. So in our renewable energy generation problem, for example, we know certain things about the problem. We know that the sun typically peaks at certain times of the day. There's a natural pattern in the data. But in ridge regression, we're simply penalizing the weights uniformly. So we might overlook domain-specific information that we could have actually incorporated into our estimation process. So this can limit ridge regression's effectiveness because it's going to treat all features as equally important because it assumes that they all weights should be penalized in exactly the same way. So ridge regression is a good start, but it's not necessarily the optimal approach. The regularization term in ridge regression is to some extent pretty blunt because it's not gonna capture the nuances of how certain features contribute to the prediction or how we might expect certain features to contribute to the prediction. So this brings us to the key point of the lecture here today, is that, could we do even better than ridge regression by incorporating, knowledge about the data generating process? Could we, are there more intelligent ways to go about regularization, to penalize those weights in a more informed way? And so, yeah, today we're going to be focusing on how to take into account that prior knowledge. And so we're going to start today in lecture 9a and then finish up in the second part in lecture 9b. And so this is going to this question of how we take into account prior knowledge is really going to break away to some extent from the philosophy that we've had in the course so far. We've been fitting our models to the training data kind of on its own terms, treating the data as kind of this closed universe, without putting these fitted models into a larger context that might have access to specialized domain knowledge. And so thinking about things this way is also going to give us an appreciation for the fact that our parameter estimates really are themselves uncertain. And so therefore the predictions that we make should also be taken with a grain of salt. And so the second question that we'll consider today is, to explore methods to quantify this corresponding uncertainty about our predictions, essentially figuring out how big that grain of salt actually is. And then in lecture 9b, we're going to consider an almost perfectly opposite situation, one where we have very little knowledge at all to solve the regression problem. Specifically, we don't even know what form of the model, what set of basis functions we can use. All right, so getting on to that first question, how can we actually incorporate prior knowledge into a model? So let's start with a motivating example. Suppose you're a data scientist working for a wind energy company, and your job is to figure out the likelihood that a given day in October is going to be windy. And for the sake of argument, let's say that windy is defined as having an average wind speed over a 24-hour period, as the wind speeds are 25 kilometers per hour or greater. And so if you could know this probability, that'd be extremely valuable because the company would then be able to forecast things like the wind energy output, potentially optimize energy storage, and might even be able to manage the distribution of energy more effectively, manage the distribution of energy to the grid more effectively. And so to model this, we can assume that whether a day is windy or not can be represented as a Bernoulli random variable. So in this case, the probability of a day being windy, we denote that as the parameter pi. And in the framework of a Bernoulli random variable, each day is either windy or not. There's no middle ground. So this means that the probability mass function would be determined entirely by that single parameter pi. And that's what we're trying to estimate. So we can do this by using the maximum likelihood estimation, where we would start with the likelihood function, which is the product of probabilities of the individual observation. But then for a concrete numerical example, let's say for 5 days in October, we observed that 2 were windy, and then 3 were not. So these observations would form the set Y, where each yi is 1 if the day was windy and 0 if it wasn't. Okay, so the next step would be to use these observations to find the MLE for pi, which is the value of pi that maximizes the likelihood of observing the data. And to simplify the math as we normally do, we take the logarithm of the likelihood, and this is going to convert that product into a sum. And after taking, and then we take the derivative of the log likelihood with respect to pi and set that to 0. And then we solve for pi to get the MLE estimate. So rearranging this equation here, we can find that the final estimate for pi is just the average of the observations, yi. And this makes intuitive sense because, it's simply the proportion of the days in which in our sample that were windy. And for this particular data set, that proportion is 0.4. So the MLE estimate for the probability of a windy day in October is 0.4. So this approach is a good example of what's known as the frequentist method, where we estimate the parameters directly from the data without using any prior knowledge or assumptions about what pi should be. Okay, but what if we already had some prior knowledge or historical data about the region? Suppose that there was some historical data that suggested maybe 70% of the days in October are windy. So for example, maybe long-term climate data for the location in which our wind ball operates shows that 70% of October days have wind speeds greater than 25 kilometers an hour. In this case, we wouldn't want to start our estimate from scratch. We'd want to anchor our estimate of pi to something close to around 0.7. So for example, I did my PhD at the University of Calgary, and in the southern parts of Alberta, there are some really windy areas, and quite a few, a lot of windmills down in like the Pincher Creek area, Claresholm, and so if you have that historical data, you wouldn't want to employ the frequentist estimate. You wouldn't want to throw out that information. So, but the question is, how can we represent that prior knowledge? So it turns out that a natural choice for modeling prior knowledge about pi in a Bernoulli model is to use a beta distribution. So the beta distribution is parameterized by 2 shape parameters, alpha and beta. And it's what's nice about this is that it's defined over the interval of 0 and 1. So this makes it perfect for representing probabilities, which also need to fall within the range of 0 and 1. And then depending on the value of these shape parameters, the beta distribution can take on various shapes. And this figure is grabbed from Wikipedia and shows the beta distribution for different shape parameters, alpha and beta. So yeah, it can take on different shapes. It can be pretty flat or symmetric. It can have skews in either direction, or peaked around a certain value. And so this gives us the flexibility to not only encode like different values of pi, but also different levels of certainty or uncertainty about pi. Okay, and so it turns out that the expected value of pi is given by alpha over alpha plus beta. And so that would be the mean of the beta distribution. And then the plot on the right here shows three different beta distributions with varying parameters, but they're all centered around 0.7, which is what our historical data would suggest. And so for each of these plots, alpha over alpha plus beta was equal to 0.7. And so if we were to set, for example, alpha to 7 and beta to 3, we'd get this gray curve here. So yeah, it's got a mean of 0.7, but it's got a modestly wide spread. So this would indicate some uncertainty around that central value. And then if we were to increase alpha and beta to 70 and 30 respectively, then we'd get the blue curve. And this would make the distribution much more concentrated around 0.7. So we'd be more confident. This would indicate greater confidence in our prior belief. On the other hand, if you shrunk alpha and beta down to something like 0.7 and 0.3, you'd get a distribution that's still centered at 0.7, but now has a bowl shape and actually has some bimodality. So this would suggest that, not even quite sure what the exact physical interpretation of pi would be in this case, but it would be extreme uncertainty around a mean value of 0.7. But yeah, perhaps let's take alpha as equal to 0. Alpha as 7 and beta as 3 to represent kind of modest uncertainty around that value of pi. Okay, so we've represented the prior knowledge, but now we need to incorporate it into our estimate of pi. We need to kind of merge our observations with that representation of our prior knowledge. And so in machine learning, Bayesian updating is a process that allows us to do that. So we combine our prior beliefs captured by that prior distribution with evidence from the data captured by the likelihood function. And then what we do, and then when we do that, we obtain a posterior distribution. So this posterior distribution tells us how likely different values of pi are, given our prior knowledge of pi, and then the observed data, the likelihood. So yeah, this equation at the top here shows the key idea of Bayesian updating. Posterior distribution of pi, given the data, is proportional to the product of the likelihood and the prior. So this tells us that the posterior combines our initial beliefs with the information that with the insights that we gained from the data. And so for our Bernoulli beta model, we would have that the posterior distribution is proportional to the likelihood of Bernoulli multiplied by the beta distribution, and then we would sub in sub in our expression for the likelihood and the beta distribution that we had before. But to simplify, we can simplify the math in here a little bit by introducing a binomial random variable. And this is going to represent the number of windy days out of n total days. So using the binomial distribution, we can write the likelihood of observing k windy days out of n as a function of pi. And yeah, so when we multiply this likelihood, so now we can swap that in down here. When we multiply this likelihood with the beta distribution, beta prior distribution, we would now end up with a new beta distribution that reflects our updated beliefs about pi. And so, yeah, now we would get new shape parameters based on the old shape parameters, alpha and beta, plus the counts of windy days k, and the total number of days n. So yeah, this is what we mean by posterior update. We've incorporated new data by adding these counts to our prior beliefs. So a couple things to note, because we're dealing with a Bernoulli random variable and using a beta prior distribution, the resulting posterior distribution is also going to have a beta form. So this is because the beta distribution is what's known as conjugate to the Bernoulli. And what this means is that the product of the likelihood and the prior is another beta distribution. And so working with such conjugates makes the math a lot simpler. It's worth also noting that a full Bayesian update would also involve normalizing the product of the likelihood and the prior to ensure that it represents a valid probability density function. But today we're only interested in determining the value of pi that maximizes the posterior distribution, known as the maximum a posteriori or MAP estimate. And so we can ignore the normalizing constant that would have appeared in the likelihood as well as the beta distribution. And so yeah, this key takeaway message here is that Bayesian updating allows us to refine our estimates in a principled way. So it gives us a more nuanced understanding of the probability of windy day, given both historical data and the newly observed data. But yeah, what happens exactly when we combine our prior knowledge about the probability of a windy day, which we denote as pi, with the newly observed data using this Bayesian update? And so, yeah, the equation at the bottom here shows how we can interpret the posterior distribution that we obtained as a beta distribution with new shape parameters that are determined by adding the counts of windy days as well as the total number of days to the shape parameters of the prior. And so, yeah, and then in the plot on the right here, this is the distribution of our prior, where we set alpha to 7 and beta to 3. So that had a mean value of 0.7. And then the red dashed line indicates the mean of the data we observed. And then after combining the prior and the likelihood, we get the teal colored posterior distribution. So we can see that it's been shifted compared to the prior. So it's closer, it's in between where the data was and where our prior was. So it retains some influence from both the prior belief. So yeah, it's a good example of how Bayesian methods allow us to balance our prior knowledge and new data, and particularly useful when the um, when the amount of data is limited, or we've got noisy estimates, noisy data. And so with this posterior, we can use this posterior to select a value of pi, and select a value of pi, and then be able to generate subsequent predictions. And so this process is called maximum a posteriori, or the MAP estimate. It's the value of pi that maximizes the posterior distribution. In other words, it's just the value of the value of pi, where the posterior is at its peak. So it's the most likely estimate of pi given the observed data in the prior. For the beta distribution, this peak is the mode of the distribution, and it's determined by the shape parameters of the prior alpha and beta. So it turns out that the mode of the beta distribution is given by alpha minus 1 over alpha plus beta minus 2. So this is just a standard definition for the mode of a beta distribution. So if you know this value alpha and this value beta, then you can just analytically compute the mode. But then for our new posterior distribution, our shape parameters are alpha plus k, and then the beta was n minus k plus beta, and so our new mode would be given by this expression here. Yeah, have a nice closed form solution for finding the MAP estimate. And so in this curve here, it's important to note that the mean of the beta distribution is which is given by this light teal curve, or light dotted line on the slightly to the left here. This is the mean of the beta distribution. That is not the mode of the beta distribution, which is given by this dark line here. And this is because the beta distribution is in general skewed, and the mean is not equal to the mode when the distribution has some skew to it. This is in contrast to cases where the distribution is symmetric and unimodal, like the Gaussian. In that case, the map of the mean would be the mode. But for asymmetric distributions, they can differ. So we can also incorporate priors for linear regression using maximum a posteriori. And so to see how, let's first quickly revisit the maximum likelihood estimate that we derived a few weeks ago. So the derivation involved seeing the outcome y as a set of fixed, not as a set of fixed values, but instead of y as a random variable that follows a normal distribution. But where the mean of that normal distribution wasn't just a constant, it was a function of another random variable x and the parameter vector w. So we modeled the mean as the inner product of w and x to align perfectly with our linear regression setup. So we essentially said that each observed value y is generated from this normal distribution centered around our predictive value, plus some normally distributed noise that accounts for the variability around that line. We then took the next step of constructing the likelihood function that captures the probability of observing our data given the parameters w and the variance sigma squared. And then our goal with MLE was to maximize this likelihood, which was the same as finding the set of parameters that make the observed data most probable under the model. And then, I'm not gonna go through this again, but it turned out that through MLE, we've recovered the minimum least squares objective. to obtain a point estimate for the parameter vector that we could use in subsequent predictions. So least squares can be derived through MLE by assuming normally distributed errors. And so maximum a posteriori is similar to maximum likelihood estimate in that they share a common goal. Both aim to find the best possible parameter values that explain the data. In MLE, the focus was on maximizing the likelihood function, which was based only on the observed data. But in maximum a posteriori, or MAP, this goes a step further by considering not only the data, but also the prior beliefs we might have about the data. So yeah, maximum posteriori. So whereas MLE maximized just this quantity, MAP is going to maximize the posterior distribution. So in linear regression, we need to also incorporate a prior distribution over the weights, and which are represented by vector W. So a common choice for this prior distribution is a multivariate Gaussian or normal distribution. So this distribution, we would center it at 0, which means that before we've seen any data, we expect the weights to be around 0. We don't expect them to be biased on one side or the other. And so, in addition to this mean of 0, we also have a covariance matrix denoted by capital sigma. And so this matrix would control how confident we are about our prior belief. And so if the values of sigma in here are small, this means that we believe strongly that the weights should stay close to 0. But if the values are large, we would allow for more flexibility. So we would be open, we would expect weights to vary more. So this prior represents our belief that the weights should be close to 0 or around 0. And then depending on how large or small the entries in sigma are, then that determines the flexibility. And the way that we can expand this prior to the probability density function using the parameterization, using the expression for a multivariate Gaussian distribution that we went over in the maximum likelihood lecture. So the probability of observing so that's the prior. So now let's consider the likelihood function and probability of observing the labels y, given the features in the matrix x, the weights w, and the variance of the noise, denoted by sigma squared. And so in this case, we're treating the entire vector y as jointly Gaussian. So we're not treating each observation in y independently. Instead, we're treating the entire vector y as a whole. So this is going to give us a multivariate Gaussian likelihood. This is just a generalization of the regular Gaussian distribution, but it applies to vectors instead of single values, as we saw in the lecture on MLE. Okay, so let's now get into how we can incorporate a prior into linear regression using the map estimation. So we first start off by combining our likelihood and our prior. And yeah, the likelihood is all about the data. It tells us how likely the data we observed is given the weights. And then the prior, on the other hand, reflects what we believe about the weights before seeing the data. And so when we combine these, we get the posterior, which is the probability of the weights given the data. All right. So to make To make things simpler, we take the logarithm of this whole expression, and that's going to turn the product into a sum. And uh, yeah, and then as taking the log doesn't affect where the maximum occurs. We haven't changed the objective, and I've also skipped over omitted some constant scaling factors that won't change the position of that maximum. Okay, and so that brings us to this expression here. Uh, yeah, in this fourth line here, so we were maximizing a sum of two negative quantities, and now we're going to minimize the sum of two positive quantities, multiplying through by two because that appears in both places. Um, and yeah, I'd like to draw your attention specifically to this part here where we have the inverse of the covariance matrix sigma. And so this is how we represented our belief about how much the weights should vary. So let's simplify things a little bit more. Let's assume that sigma inverse is a diagonal matrix. So in this case, we're saying that we also don't expect the weights to influence each other. So they're independent. So they don't covary. So in this case, sigma inverse would be a diagonal matrix. So it's an identity matrix where each element along the diagonal has a value of some lambda. And so if we do that, we can make things quite a bit simpler. Yeah, we can rewrite this expression here as a sum over the errors, and then plus the norm of the weights scaled by lambda. And so this brings us to something familiar. Now this is ridge regression. So when we assume that the weights don't covary and the inverse covariance matrix on the prior is diagonal, we've recovered the ridge regression objective. And so why does this matter? Well, we already know that ridge regression or L2 regularized linear regression, we've already seen that before. Ridge regression modifies the ordinary least squares objective by adding a penalty on the size of the weights. And this penalty is important because it prevents the weights from becoming too large. This can help us avoid overfitting, especially when we have lots of features or potentially highly correlated features. And that the amount of regularization was controlled by lambda, but now, instead of seeing lambda as something that we kind of randomly or arbitrarily added to control overfitting, we now see that it actually comes from a prior belief that the weights should be small, centered around 0. So that's pretty cool. So yeah, to come back to our ridge regression fits on the renewable energy generation data, within this Bayesian framework, ridge regression isn't just some arbitrary trick. It's the result of placing a Gaussian prior on the weights. And so the regularization term can, is effectively a reflection of our prior belief once we interpret it within that probabilistic lens. But what's really neat is that with Bayesian thinking, our priors can be a little more nuanced or more intelligent than blunt penalizing of weights that ridge regression achieves. So specifically, we can structure a prior to have a mean vector other than the 0 vector. We can tweak elements of the covariance matrix to reflect our certainty in various quantities, for example. So let's say that we had a we had a strong belief that uh, one of the uh, one of the basis functions should be negatively should have a negative contribution to energy generated. We could specify that in our prior, or maybe another one should we expect that to have a positive contribution to the energy generated. We can incorporate that in our prior, and then but leave the other ones to zero. Uh, we can and then we can reflect different levels of confidence in this in our covariance matrix. So uh, elements along the diagonal of the covariance matrix, if they're small, that would indicate greater confidence in those estimates. Whereas if we don't have strong beliefs about what those coefficients should be, we can leave those respective variances large. And so now we can compare the use of the map prior, that intelligent prior, using map on our data set. So yeah, quick recap. Yeah, because the MLE estimate didn't incorporate any prior knowledge, we saw that it overfit on small data sets. Ridge regression fit did a little bit better. The regularization helped control the amount of overfitting. But then the map estimate in these purple lines here, we see that yeah, because it reflected not just the data but also our prior belief, it seemed to do a better job of more often capturing the qualitative shape of the true underlying distribution than of course either the unregularized solution or the MLE estimate. And so, yeah, the benefit of incorporating these flexible priors is that they allow us to inject domain knowledge or beliefs into the model. So if we knew that energy generation tends to peak at certain times of the day, we can impose those priors that reflect that behavior to result in more realistic predictions that generalize better when the data set is small or noisy. Yeah, this can be particularly beneficial when there's high variance in the data or when we're working with very few observations. Yeah, there is, however, a very serious catch in that if we use the wrong prior, you could seriously mess things up. A prior that doesn't align well with the actual underlying pattern could bias the model in a way that degrades its performance, maybe even making it worse than a model that only used the data. And so in those cases, MLE using simple ridge or lasso regularization would be safer choices because those methods don't impose any strong external beliefs or rely solely on the observed data. So those wouldn't be prone to the risks of a poorly chosen prior. So yeah, the key takeaway is that these methods should be used sparingly in situations where you have strong prior beliefs and you have little data to work with. Then MAP can be more robust, can produce more robust results than MLE. So yeah, we've been talking a lot about probability today, and we've seen that we've seen that our estimate for the parameter is really just one over a distribution of parameters, and so we want a way to account for this uncertainty in our parameters. The fact that these point estimates that we've been working with don't capture the whole picture of what's going on. And so, yeah, crucially, the approaches that we've talked today, maximum likelihood estimate and maximum a posteriori, both of these methods give us what we call point estimates of the weights. So they give us just one set of weights that we believe is the best explanation for the data. So this is in line with classical linear regression. So we assume that there's just one true set of weights out there that perfectly explains the relationship between the inputs and the outputs. And then we make predictions based on this single point estimate. So we've effectively assumed that this optimal weight vector captures all the information needed to model the data. But this approach doesn't account for any uncertainty in the weight estimates, and this can lead to overconfident predictions or poor generalization, especially when the data is sparse or noisy. There's an alternative to this, and one alternative is called Bayesian linear regression. So here, instead of assuming that there's one set of perfect weights, it acknowledges that there's uncertainty in the data and the weights. So it treats the weights that we'll call W not as fixed values, but as a random variable that follows its own distribution. So rather than betting on a single set of weights, we think of weights as a whole range of possibilities. And so how it works in Bayesian linear regression is that we learn a distribution over possible weight values from the data, rather than just one. Specifically, when we make predictions, we're averaging over all possible weights, weighted by how likely each weight is according to the data. So it's kind of like hedging your bets. You're not putting all of your money on one stock, but you're spreading it out across several stocks based on how well you think each one's going to do in the long run. So this distribution over weights is called the posterior distribution over W, and it represents what we believe about the weights after we've seen the data. So the posterior distribution, in turn, is written as probability of W given X, observed data X, the features and the labels Y. So this tells us how likely each possible set of weights is based on the data we've seen and our prior beliefs about the weights. If we assume a Gaussian prior, for the weights, specifically a prior on W with zero mean and some covariance matrix, as we just did, and that the likelihood also follows a Gaussian, then the posterior distribution is also going to follow a Gaussian, but with a different mean W bar and a precision matrix A, which is the inverse of a covariance matrix. We're not going to get into the weeds here today, but it turns out that the posterior mean W bar can be computed using the training data scaled by the noise of the observations and the posterior covariance that I'll get to next. So this W bar is the center of the multivariate Gaussian, defining the posterior distribution of the weights. So if we were to draw many random samples from this distribution, we would expect to see samples close to this mean most of the time. And so the posterior precision matrix alpha, this is in turn a sum of two terms. So one is a contribution related to the data, X transpose X, and then scaled by inversely proportional to the noise of the observations. And then the other part comes from our prior belief about the weights, represented by capital sigma inverse. So our final uncertainty about the weights combines what the data tells us and then what we initially believed. So whereas the posterior mean told us about the center of the distribution, the posterior prediction tells us about the spread of the distribution. So this would capture the confidence about the weights. So yeah, if the elements of this precision matrix are large, it would mean that we're very certain about the weights. And then if they're small, it would mean that we're very uncertain. All right, so putting this all together, the posterior distribution follows a normal distribution with a mean of W bar, and a covariance matrix that's the inverse of the precision matrix A. Okay, so to emphasize the difference between classical and Bayesian approaches to parameter estimation in the context of a linear model of the form y is equal to W0 plus W1x, let's visualize how the prior and posterior distributions change as we observe new data points. To illustrate this, let's consider a synthetic data set generated from a function with true parameters W0 of minus 0.3 and W0 and W1 of 0.5, indicated by this white plus marker down here. So our objective is to see if we can recover the values of W0 and W1 using Bayesian inference. So in this figure here, which is taken from Pattern Recognition and Machine Learning, section 3.3, we start by plotting the prior distribution in weight space before any data points are observed. So in this case, we have a mean of 0, and then we've also got some. It's an isotropic Gaussian, so it's following sigma in all directions, regardless of where we look. And then the weights don't covary. The off-diagonal elements in this covariance matrix would be 0. If we were to draw samples of W from this prior, then we could we could plot a few regression lines. We would some regression lines would be negative, some would be positive. We'd have some high bias, some negative biases. Clearly there's a wide spread. So we're initially very uncertain about the weights and what the function actually is. Okay, and so in the second row now, we're going to see what happens after we observe just one data point. So this is our likelihood function now. So if we observe one data point, specifically x of 0.9 and then a y of 0. So there's many possible sets of weights that could explain or account for that particular observation. And so this means that this is reflected by our likelihood here, having a regime of high probability. And again, the true parameter values used to generate the true parameter values that we're trying to recover are minus 0.3 and 0.5. Luckily, the data that we observed is the regime encompasses the true parameter values. Okay, so what we then do is we multiply the prior by this likelihood, and then we get a new posterior. So we can see that that first observation radically changed the posterior distribution. We're clearly seeing some covariance between the weights, and we've shrunken down made it quite a bit more concentrated, and so we're getting more confident that the weights live in this particular area. And then if we were to draw samples from the weights from this posterior distribution, now we could generate a set of regression lines, generate a new set of regression lines. Interestingly, these these now all kind of pass close to the point because we've kind of imposed a soft constraint that the regression lines must pass close to the observed point. All right, so now let's see what happens when we observe a second point. So this is in the top row is just the um, what we just had. And now the second point that we observe is this blue circle in the bottom right-hand plot. Okay, so the likelihood function, the regime, the parameter regime that could have accounted for that data is now shown here. And so this, when we multiply the posterior distribution that we just got is now the prior for this next update. When we multiply this by our likelihood, the new posterior is this plot here in the middle plot. And so the posterior has become a lot more concentrated as it now incorporates information from the two data points that we've seen before. So this is a lot more precise estimate of the underlying parameters. And now if we were to sample regression lines, sample parameters from this, we would get regression lines that all pass close to both observed data points. So we've got an even further refined belief about the linear model. Okay, so now and then the effect of observing a total of 20 data points, it shows the likelihood function of the 20th data point alone. And then in the middle, we've got the final posterior distribution, which has merged information from all 20 observations. So you can see that the final covariance is a lot more compact. It's shrunk down to almost a single point. And it's very close to the true parameters, which is the key takeaway here. So yeah, shrinking the posterior down reflects our increased confidence in the parameter estimates. And now if we were to sample weights from this distribution, we can see that the lines now follow closely the trend defined by these 20 data points. So the model's done a pretty good job of capturing the underlying relationship in the data. Okay, so as I said, in Bayesian linear regression, we're interested in estimating the probability of observing a particular response given some input. And so this was the crucial difference from linear regression. We don't compute a single point prediction. We compute a distribution over possible predictions. So this distribution can be used to generate confidence intervals, quantify uncertainty associated with prediction. So Bayesian linear regression provides a more nuanced understanding of the predictions by incorporating uncertainty. Okay, so let's let X star be a d-dimensional input vector about which we'd like to compute the probability of an estimate, probability of an output that will denote Y star. So X star is our kind of test input, and then we're interested in the probability of a particular output Y star. And so this whole thing is going to output a scalar quantity on the real number line that corresponds to the probability of seeing a particular output given this particular new input. And so computing this predictive distribution over Y star requires the new input X star and the training data matrix X. And that's going to have n rows and d columns, and then the vector Y, which is going to have n elements. And so in terms of how this is done, this is done by a weighted average over all possible models, specifically by integrating over all possible values of the weight vector W So this first term in the integral, probability of y star given x star and w, that's the likelihood function. So it describes how likely the new output y star is, assuming a fixed factor w and the new input x star. So this term represents the expected output value based on the linear relationship defined by w. So this second term, probability of w given x and y, this is the posterior distribution of the weight factor given the observed data. So this term tells us how likely a particular weight factor is given the training inputs x and the outputs y. And so by integrating the product of these two terms over all possible weight factors, we're going to obtain that new posterior predictive distribution over y star. So this integration is going to allow the model to take into account the entire distribution of possible weight values when making predictions, rather than relying on a single point estimate. So that this posterior predictive distribution is going to capture the uncertainty in both the observed data and the model parameters. So the predicted value for y star, crucially, that's not going to be a point estimate. It's a distribution that reflects a range of possible outcomes and their relative probabilities. So for our model, the likelihood function captures the probability of y star given x star and w. And since the noise of the observations is assumed to be Gaussian with variance sigma squared, the likelihood is a Gaussian centered at x star transpose w with a variance of sigma squared. So this means that for a fixed weight factor w, the likelihood function tells us how likely a particular y star is, given the linear relationship defined by w and the known noise in the observations. And then the posterior distribution of the weight factor w given the training data x, that's what we derived a few minutes ago. This is the posterior distribution that tells us how likely different weight vectors w are given the observed data. And so we know this is a Gaussian because both the prior on w and the likelihood on w were Gaussian, so the posterior distribution is a Gaussian as well. And then this is parameterized by its mean vector w bar and the precision matrix A, which was the inverse of the covariance matrix. And so, by combining the likelihood and likelihood over the weights through this integral, it can be shown that the resulting predictive distribution is itself a Gaussian with a mean equal to x star transpose w bar and a variance that combines the observation noise sigma squared with this additional term that depends on the posterior precision matrix. So this which accounts for the uncertainty in the weight estimates. So this means that the more uncertain we are about the weight factor, the larger predictive variance for y star will be. So this integration process can be interpreted as a convolution between two Gaussian distributions. So the Gaussian likelihood and then the Gaussian posterior distribution over the weights. And then just to sum up, by combining the likelihood and the posterior distribution through this convolution, the predictive distribution is also a Gaussian that captures both sources of uncertainty, the noise in the observations and the uncertainty in the weight estimates. So we're going to be making the predictions are not just point estimates, but come with uncertainty estimates as well, providing more nuanced understanding of the model's predictions. All right, so that brings us to the end of part A of this lecture, and we'll see you back here next time for part B.